because we may have to go over it. All right. So our first approach to this might be to say, well, let me bust out my graphing calculator and I can find the max and min straight off the graph. And there's nothing wrong with that except one small thing, and that is that we know that calculators can lie. Right? So it's possible that I could get a point that is close to, but not exactly equal to the max or the min. And the second is that I can't really justify an answer by saying, well, I looked at the calculator and there it is. That's not really a justification. So if I want to be able to justify my answer, I need something that is going to guarantee that my absolute max really is the absolute max, and then my absolute min really is the absolute min. And so I'm going to go back to some of the stuff that we did over Christmas. Let's take a look at what a graph of our function would look like. And what's the y value right here that corresponds to -2? What's the y value that corresponds to -2? Which is 4. Exactly. I wanted a real number here. Okay? And this guy, of course, is 1. Looking at the graph, I strongly suspect that my max is what value? 4. And I strongly suspect that my min is what value? 0. Yeah. So the graph is telling me some things, and I think it's probably right, but how do I justify it? Notice that I really only have 3 candidates for maxes and mins. 2 of those candidates are the endpoints of my interval. And the third candidate is the one point in the middle that is a local max, local min. Do you see it? And that local min could possibly be my absolute minimum. How do I find local maxes and local mins? If you remember, before Christmas, we had a theorem. And our theorem was that local extrema only occur at critical points. Places where either we have a horizontal tangent line or the derivative fails to exist. So, the theorem that is going to drive our method is that local extrema only occur at critical points, and critical points come in 2 flavors. Places where f prime of c is equal to 0, or else where f prime of c fails to exist. How do I know that a local max or min can't occur at some other point? Well, what are my other options for f prime? F prime could be positive, or it could be negative. If f prime is positive, what do I know about my curve at that point? If f prime is positive, what do I know about the curve of f at that point? It is increasing. And if it is increasing, it can't possibly be a local max. And it can't possibly be a local min either, because points to the left will be below. Or f prime could be negative, but if f prime is negative, my curve f is doing what? Decreasing, and it can't possibly be a local max or a min. So the only places where local maxes and mins can occur are either going to be places where f prime is equal to 0, or else where f prime does not exist. And so this now gives us a method, which is the critical points endpoints method for finding local extrema. Here's how we're going to do our critical points endpoints method. First of all, we're going to find the critical points. We're going to identify or ID the critical points by setting f prime equal to 0, f prime does not exist, and see what we can find. Second, Having identified the critical points, we're now going to do something very simple. We're going to evaluate our function f at the critical points and also at the endpoints. Now, why do we include the endpoints? Well, we include the endpoints. The endpoints cannot be local extrema, but they could be absolute extrema if my function increases all the way up to the endpoint or decreases all the way up to the endpoint. The largest of my function evaluations is necessarily the absolute maximum. Why? Because if the absolute max occurs, if it's at the endpoint, fine. If it's not, it's in the interior, which means it has to be a local max. This is it. We identify the critical points, we evaluate after the critical points, and we take the largest and smallest values. Okay, so let's actually do that with our function up here. Walk through and see how we get these candidates and see what we do with them. Hi. Glad to see you. Recall that our function was f of x equals x squared on the closed interval -2 to 1. And we're trying to find the absolute extremity. So now we're going to first identify the critical points by setting f prime equal to 0. And when we set f prime equal to 0, to nobody's great surprise, what solution does this equation have? X equals 0. And so this is our critical point. I could also set f prime does not exist. But there is no solution here. If you omit this guy right here on paper, but you do it in your mind, that's actually okay. Nobody needs to see that really. But I put it here just so that you can be clear about the thought process. We want to check both of those possibilities at all times. Now that I've found my critical points, I'm going to evaluate f at the critical points and at the endpoints. Here are my two endpoints, and here is my critical point. Notice I'm not evaluating f prime. I'm not interested in the value of f prime at these points, the slope. I'm interested in the actual value of the function because I'm looking for the largest value of the function and the smallest value. And when I evaluate f of -2, I get 4. When I evaluate f of 1, I get 1. And when I evaluate f of 0, I get 0. And that's it. Here, these three values are called the candidates. And your candidates are critical points and endpoints. And that's it. Now that I've evaluated here, I can take a look and I can say, which one is the largest of these? 4. And which one is the smallest of these? 0. And so just as we suspected from the graph, we can say that the absolute max is f of -2 is equal to 4. Notice how I expressed that. I expressed that in such a way so that I'm saying what the max is. I'm also telling you where it is located. It is located at x equals -2. The maximum value is 4. The largest value of the function is 4. And the absolute min is f of 0 equals 0. The justifying work that justifies all this is the finding of the critical points, the finding of the candidates, really, and the evaluation of the function at the candidates. that process make sense to everybody? All right, let's try it. Find the absolute max and min of quick check. Am I wasting my time? Am I guaranteed that this function has an absolute max and an absolute min? Because it is, yeah, because it's continuous on the closed bounded interval 1 to 2. It has an absolute max, it has an absolute min. Find them. Go. What's unusual about this function? It has no critical points. That's very good. It has no critical points in the domain that we're talking about. What does that mean about my candidates? The endpoints only. That's exactly right. If a function is always increasing or a function is always decreasing, then it's going to have no critical points, and it's going to have only the endpoints as the candidates, which makes a lot of sense. It's always increasing by minimum, because on the left, it's back to the right. So hopefully, all of you got to this point just like this. This is an elegant way to write what we're talking about. I have a derivative. I set it equal to 0 because I'm supposed to. But I recognize there is no solution. So I acknowledge that fact straight up. And so I then can identify my candidates x equals 2. I should also consider where f prime does not exist. And that would be at x equals, where does f prime fail to exist? 0. But that's outside of domain, so I'm going to ignore that. So my candidates are x equals 1 and 2. I compute f of 1. Please note I am not computing f prime of 1. I'm computing f of 1 because I'm looking for the largest and smallest values of the function f. And f of 1 is equal to 1. f of 2 is equal to 1/2. And so I can label this guy as my absolute max, and I can label this guy as my absolute min. And I've got a solution. Any questions about the process? Question?
Yeah. I know.
Let's do this. No? Wait. I did this wrong.
Oh yeah,
Sorry.
I think so.
Good. That's fine. E to the negative x. Forget your product rule when you take the derivative. First times the derivative of the second plus the second times the derivative of the first. Now I end up with an interesting problem. How do I solve this equation? Yes, factoring is your friend. I have a common factor of e to the negative x, and out it comes. And so this gives me two possibilities. The first equation has no solutions because an exponential is always positive. The second equation has a single solution, x equals 1. This gives me a critical point, x equals 1. And so now my candidates are the critical points and the endpoints. I usually do them in numerical order. But you can do them in any order you wish. What is f of 0 equal to? 0. What is f of 1 equal to? Are you sure? Isn't it e to the negative 1?
Yeah.
Yep. And what is f of 4 equal to? 4 e to the negative 4. That's exactly right. Which one's largest? Which one's smallest? F of 4 is largest?
Oh no, when you put it to negative 4, I put the one largest.
Smallest, 0.
What does a negative exponent mean? It means a reciprocal, right? So I probably had better rewrite this in order to see more clearly which value is largest and which one is smallest. Which one is going to be the largest and which one is going to be the smallest? Let's identify the smallest first. Which one is the smallest?
That's the one.
0. 0 is smaller than any positive number. So my absolute min is right here. And which one is the largest? F of 1, which is 1 over e, is larger than 4 over e to the 4th. How do I know? Well, let's do some estimating. E is about what number? About 3, a little bit smaller than 3. So f of 1 is about 1/3, and f of 4 is about 4 over, let's see, 3 to the 4th would be 9 squared would be 81. 4 over 81 is about 1/20th. So definitely, this guy is the largest right here. Does anybody need me to go over the numeric part, the very last bit again? How we did that? Yeah? Okay. So the first thing is these negative exponents are going to confuse me, so I rewrite them in terms of reciprocals. So I'm looking at all positive numbers. Then I remember that negative numbers are always less than 0. 0 is always less than positive numbers. So there's my absolute min. And then I have to compare these two, so I can make a rough estimate. E is about 3. So this guy is about 1/3, and this guy is about 4 over 81. And I think it's pretty clear that 1/3 is going to be a lot larger than 4 over 81. I'll put up a video about optimization. Optimization is going to be doing exactly this in a word problem context. And we're going to be spending the next few days on optimizing. I know that I did not, as promised, make you write down the extreme value theorem because we ran out of time. Trust me, I have not forgotten. So I'll be sending you a class near you. And I'll see you tomorrow.
That's it? That's it?
So,
Oh my God.